We're getting ready to start the engines and begin our tutorial flight, but before we do that, let's take a quick second to discuss the bleed air system of the 737. To start, let's get the APU fired up. We've accomplished a fire test, so we'll start the left forward fuel pump and select the APU switch to start. A quick note about the fuel pumps. The center tank fuel pumps cannot be selected on whenever AC power is being transferred. The APU is typically run off of the left forward fuel pump. While the APU can suction feed fuel, it is better for the life of all system components if it is provided fuel under pressure from the left manifold. This can be via either the left forward, left aft wing tank pumps, or the left center tank pump. However, keeping in mind the restriction on transferring AC power with a center tank pump on, we generally start the APU on the left forward fuel pump. Once the APU is started and the APU generator off-bus blue light illuminates, indicating that the APU is ready for electrical load, we can check the quality of the power and select the APU generator on. We should now start a timer for 2 minutes so that we can allow any oil, hydraulic fluid, or de-ice fluid trapped in the APU system to be burned off prior to introducing APU bleed air into the cabin and cockpit. At this point, if center tank fuel is present, we could use the center tank left pump to feed the APU and turn off the left forward wing tank pump. This would keep a fuel balance from developing. For today's flight, we don't have center tank fuel, so we'll just leave the left forward pump on. Let's take a quick look at the bleed air panel itself. This panel is often considered the bane of a 737 first officer's existence, but it's really not that difficult once you learn the ins and outs of how the panel works, as well as some system logic. The first thing to realize is that the system schematic is drawn on the panel. The manifold can be thought of as two separate sides connected by an isolation valve. The right side is quite simple. An engine bleed from the right engine, powering wing anti-ice, and the right air conditioning pack. The isolation valve isolates the left and right sides of the manifold. The left manifold similarly has the left engine bleed, powering the left pack and left wing anti-ice. The only addition is the auxiliary power unit bleed, which can also power the left side of the manifold, or the right side through an open isolation valve. There is a check valve here between the APU bleed and the engine bleed that keeps high pressure engine bleed air from flowing backwards through the system and potentially damaging the APU. Let's talk about the system logic. The isolation valve in the automatic position is typically closed. This assumes that the four corner switches, being left and right engine bleed and left and right pack switches, are in their normal positions. Normal being on for the engine bleeds and auto or high for the packs. 2 minutes have elapsed, so let's turn the APU bleed on and demonstrate this logic. This is the standard configuration for the APU panel while running off of the APU bleed. The APU bleed is on, as well as the engine bleeds. The left and right packs are both operating in the automatic position, and the isolation valve is manually opened. Let's put the manual isolation valve switch to the automatic position, and we'll allow the system logic to take control. Here we can see that, as previously discussed, The isolation valve is closed since the 4 corner switches are in their normal positions. If we take any of the 4 corner switches and move it to an abnormal position, i.e. off, we'll see that the isolation valve will open. The left and right sides of the manifold are now being pressurized by the APU bleed through an open isolation valve. The same is true if we turn off the left engine bleed. Again, the left and right manifolds are pressurized equally by the APU bleed through an open isolation valve at roughly 20 psi. The same is true if we turn off a pack. The left and right manifold needles are pressurized equally because the isolation valve is open. Interestingly, though, the pressure is up around 40 psi, and the reason is this. When either pack is selected off, the remaining pack is driven automatically to the high position, indicated by the higher pressure. If we return the left pack to its normal position, putting all 4 corner switches in a normal position, the isolation valve will close. The right side of the manifold is unpressurized because the right engine is off, and the left side is being pressurized by the APU. For this reason, on the ground, we manually open the isolation valve to provide APU bleed air to both the left and right packs. The final note is the dual bleed light. The dual bleed light simply indicates that the APU bleed is on, and in the event of a check valve failure, could be damaged by high pressure bleed air from either the right or left engine bleeds. The system logic is purely driven off switch position and not valve position. Let's take a look at this and see the different ways to extinguish a dual bleed light. If we close the isolation valve and isolate the left side of the manifold, then it becomes relatively simple to extinguish a dual bleed light. Simply either turn off the APU bleed or the engine bleed. It becomes slightly more complicated with the isolation valve open. At this point, turning off the right engine bleed does not turn off the dual bleed light because the left engine bleed could still damage the APU. Selecting both engine bleeds off will turn off the dual bleed light. We can see here that turning on the right engine bleed with the isolation valve open allows the right bleed to potentially damage the APU, unless the isolation valve is manually closed, in which case the dual bleed light extinguishes. This is far from a comprehensive tutorial. However, keep in mind the bleed air panel is relatively simple if you keep in mind the 4 corner system switch logic, the isolation valve function, and the fact that the manifold is divided into a left and a right side.